moment a rocket lifts off, it is tracked and monitored. All vital performance characteristics are relayed back to the ground via telemetry. At huge distances, a probe must be able to communicate. On Earth, to pick up these signals, we use parabolic dishes. They range in size from small domestic units for television reception to the giants of the deep space network. Without these, almost any space flight would be pointless. The very first artificial satellite, Sputnik, was designed with 4 whip antennas and 2 radio transmitters. Soviet engineers saw its main function as announcing to the world that it was there. It transmitted a continuing series of beeps. Ham radio operators around the world could detect the signal. Very few realized that the beeps varied in duration according to the temperature and pressure within the sphere. The signals could also be analyzed for clues to the ionosphere's electron density.
Roger, the clock is operating. We're underway.
Soon, cosmonauts and astronauts were orbiting the planet. When John Glenn made the Mercury program's first orbital flight, 18 different tracking and communications posts were set up along his spacecraft's ground track. As well as local staff, NASA provided each ground station with its own capsule communicator, a flight engineer, and a flight surgeon. Special tracking ships were deployed to maintain communications and monitor telemetry while the spacecraft was crossing the ocean. But even so, the network had blind spots where the spacecraft was out of reach. For the Soviets, communication was even more difficult. During their early space flights, there were no tracking ships, and their terrestrial stations were all in the Soviet Union. When the Soviet Union launched Lunik 1 in 1959, it was intended to hit the moon. It missed and became the first craft to achieve solar orbit. Because it required special tracking infrastructure and was not monitored outside Russia, many in the United States refused to believe that the spacecraft had even been launched. At the time, the world's largest radio telescope was the Mark I installation at Jodrell Bank in the UK. Soon the Russians began sending detailed information about finding their probes to Jodrell Bank as a means of independently verifying their missions. In the early days of the space race, the Soviet Union had big plans for deep space missions. In 1959, construction work began on the Pluton facility in the Crimea. Though the Soviets did not enjoy the financial resources of the United States, they were not lacking in enterprise. The Pluton receiver consisted of 8 dish antennas welded onto pieces from the hulls of 2 war surplus submarines. They were mounted on a steerable frame made from the trusswork of a railway bridge. To point the dishes with accuracy, the designer, Evgeny Gubenko, employed the mechanism from the gun turret of a scrapped battleship. The system worked well and remained in service till 1978. It had become clear to the space powers that communications support for low Earth orbiting satellites was very different to that needed for probes traveling into deep space. Deep space missions require much larger, more sensitive dishes with powerful transmission capabilities. Yet these probes' position in the sky changes more due to the Earth's rotation than it does because of the craft's speed. So while the dish has to point with great accuracy, it does not have to move very rapidly. Satellites in low Earth orbit pass close, so a smaller dish is adequate. But it must move rapidly to maintain a precise focus on its target craft. In the United States, corporations were taking an interest in a huge new type of satellite. Researchers were interested in using an orbiting balloon to relay radio signals across continents. Project Echo launched its first inflatable satellite in 1960.
This is President Eisenhower speaking.
A telephone call from President Eisenhower was relayed from Washington to California by bouncing signals off the balloon, which acted as nothing more than a reflector. In 1962, US phone company AT&T built Telstar. It was the first electronic relay satellite. Launched by NASA in July 1962, Telstar was the first commercially funded satellite. Europeans tuning in to see President Kennedy got baseball and then the presidential press conference.
I understand that part of today's press conference is being relayed by the Telstar communications satellite.
Then French singer Yves Montand sang a song to the US.
Faire son métier, le public se souvient. La chansonnette, tiens, tiens.
As far as it went, it was a success. But Telstar's low orbit meant it was only available for 20 minutes every 2.5 hours. And Telstar's life was cut short as a result of the Cold War. Both the Soviet Union and the United States had been detonating thermonuclear weapons above the atmosphere to determine whether this was a viable anti-missile strategy. From tests in the Pacific, they discovered that an immense pulse of gamma radiation triggered positive ions and recoil electrons that took out electrical systems in Hawaii and New Zealand, destroyed at least 3 satellites, and damaged several others, among them Telstar. In October 1963, US President John Kennedy added his signature to a treaty with the Soviet Union banning nuclear testing in space. The first telecommunications satellite that resembled today's technology was Intelsat-1, also known as Early Bird. It orbited above the equator at the same rate as the Earth's spin, which allowed it to hold a static position. It could relay 1 TV channel or 240 telephone calls. It was the beginning of the space business's most profitable industry. Estimates put satellite telecommunications revenues for 2019 at $2.4 trillion US. Geosynchronous orbits make ground stations much simpler without the need to track a target across the sky. Today, there are at least 240 active satellites in equatorial orbit at geosynchronous altitudes. Not all are communications platforms. Weather satellites also find this orbit useful, having an uninterrupted view of a complete hemisphere. The craft must be carefully spaced to avoid collisions and radio frequency interference. The International Telecommunications Union coordinates the orbital slots and frequency allocations, and satellites nearing the end of their useful life must retain enough fuel to boost themselves into a graveyard orbit to prevent overcrowding. There is clutter caused by spent upper stages and old satellites. Another highly specialized group of communication satellites is also stationed in geosynchronous orbit. NASA currently operates 10 tracking and data relay satellites, TDRS. Originally designed to provide a continuous communications link for shuttle missions, TDRS supports many near-Earth satellites, as well as the International Space Station, the Hubble Space Telescope, and some military applications. Similarly, ESA has launched 2 of what will be a group of 4 data relay platforms to provide a continuous link with near-Earth satellites. Instead of transmitting to ground stations, only visible for brief parts of every orbit, many satellites now send signals up to a data relay spacecraft that can see it for half of each orbit. A network of relay satellites around the globe gives continuous coverage. All major space agencies have been experimenting with data transmissions via lasers, but the EDRS system is the first commercial application of optical communications between spacecraft. Current laser communications techniques between satellites deliver data at 1.8 gigabits per second, 30 times greater than conventional radio links. However, weather-related problems inhibit reliable laser connections between spacecraft and Earth. Transmission back to the ground is via microwave radio in the Ka band. While this is fast, it is still slower than the laser data rates, but the signal can be split into several streams and sent simultaneously. Europe's Copernicus system is a major beneficiary of the near real-time data available via the EDRS system. Copernicus is an Earth observation program relying on a series of Sentinel satellites that send back continuous streams of data about the land, the oceans, and the atmosphere. The Copernicus program is not a limited project. It is designed to collect authoritative data about planetary changes over the long term. To do this, the Sentinel satellites are in low north-south orbits, allowing them to see the Earth's entire surface every 24 hours. This polar orbit is common to every Earth-observing satellite. But not every satellite has access to the EDRS communication system, nor do they generate the vast amounts of high-resolution data that requires it. Most satellites following a polar track rely on the polar receiving installations that they pass above every orbit. On the Norwegian archipelago of Svalbard, the Svalsat installation has 31 radomes to track and download data from satellites in polar orbit. To relay the information to the outside world, twin fiber optic cables, each handling 10 gigabits per second, connect Svalbard to the Norwegian mainland. Kongsberg, the company that operates the facility for the Norwegian government, runs a smaller station in Antarctica. There are close to 1,900 operational satellites in Earth orbit, with a further 3,000 still orbiting as space junk. But there are as many as 20,000 fragments from spent boosters and debris from collisions that must be tracked. Operational satellites are routinely moved when an object approaches on a dangerous course. If this picture appears crowded, it is about to become a lot more complex. The US Federal Communications Commission recently gave rocket company SpaceX approval to launch 12,000 new satellites for its Starlink broadband internet service. Current satellite internet services rely upon a very few large platforms in geosynchronous orbit. Typical users are in remote locations, and while costs are coming down and speeds are improving, latency or response time is sluggish. The Starlink model has thousands of small satellites in low Earth orbit, cross-linked via high-speed lasers. The satellites will be able to adjust their orbital path autonomously to avoid collisions. The company launched its first batch of test satellites in May 2019. The second group, launched in November 2019, consisted of 60 operational satellites. For one company to increase the number of functioning spacecraft by a factor of 6, cost is critical. The satellites are being mass-produced in a flat pack form with a single solar panel. 60 will stack neatly within the fairing of a Falcon 9 launch vehicle. The Starlink satellite design is pushing the latest technology to its limits. Links to the ground are via a phased array, enabling a steerable beam without the need for moving parts. Maneuverability comes from a Hall effect thruster using krypton as its propellant. When released from the booster, the satellites do not require dispensing hardware. They are pushed away by springs in apparently haphazard fashion. At this stage, they can even bump each other and are designed to withstand the impact.
Away from the top of the second stage. This is the highest number of satellites.
Quickly, the satellites orientate themselves and begin spreading along their orbital path. At this point, they can be seen in the pre-dawn or just after sunset. Research astronomers are not happy about the huge number of satellites soon to be in orbit. By 2024, there should be 11,927 Starlink satellites orbiting at 7 different heights. The only satellite constellation remotely similar is the Iridium Next system, with 66 satellites cross-linked via the Ka band. They're designed to provide global cell phone coverage, and in 2018, the Iridium company finished the replacement of all its first-generation spacecraft. The upgrade cost Iridium $3 billion. For 200 times more satellites, SpaceX has budgeted $10 billion. Iridium had to pay Thales Alenia to design and build 81 satellites. There are spares both in orbit and on the ground. And it had to pay SpaceX to launch those satellites in batches of 10. With Starlink, the company will take advantage of its own drive to reduce expensive launch services. SpaceX builds its own satellites and its own rockets, so it will only pay cost for hardware and delivery. Recovery of first-stage boosters is now routine, which takes a large chunk out of launch costs. And the protective fairings, always regarded as throwaway items, are now fitted with steerable parachutes for retrieval and reuse, saving a further $5 million per flight. What will give Starlink its edge is its improved latency. In most cases, the system should give even better latency figures than fiber optic connections on the ground, let alone the half-second delay built into systems that send signals 35,000 kilometers up to and back from geosynchronous platforms. For stock markets reliant on high-frequency trading, microseconds make a significant difference. SpaceX believes people around the world will want the service. OneWeb and Amazon's Project Kuiper have announced plans to develop their own low Earth orbiting broadband systems. But with just the smallest fraction of the Starlink constellation in orbit, astronomers are starting to worry. Survey telescopes that use time exposures to map the skies, looking for anomalies like approaching asteroids or exploding stars, have recorded dusk and dawn images marred by Starlink satellites. Researchers from the Large Synoptic Survey Telescope, currently under construction in the Chilean Andes, have run simulations suggesting that as the Starlink constellation takes shape, certain observation times will be unproductive. Yet the Starlink venture itself is still a risk. Satellite businesses like Teledesic and Skybridge, both with big plans, went under. And SpaceX leader Elon Musk admits that success with Starlink is far from a sure thing. Communications with very distant exploratory spacecraft are governed by different parameters. The New Horizons probe, launched in 2006, is equipped with the most advanced digital technology ever to reach deep space. While its primary target was the dwarf planet Pluto, it passed Jupiter in 2007 for a gravitational boost to its speed. At Jupiter, a mere 2.3 billion kilometers from Earth, it transmitted images at 38 kilobits per second. That's slightly slower than an old acoustic telephone modem. At these distances, signal strength from New Horizons was weak, and only the 35 and 70-meter dishes in NASA's Deep Space Network were useful receivers. Even so, the data rate was slowed to deliver a coherent signal. Sending commands to the spacecraft is an exacting process. All instruction code is thoroughly reviewed by different teams before being tested on a simulator. Only then are they sent to the spacecraft. Because the environment around Pluto was so poorly understood, controllers on the ground relied on preliminary images returned by the spacecraft to make a hazard search. Distant encounter observations commenced 7 months before its close pass. As New Horizons approached Pluto in 2015, it had at least 16 different science objectives, along with spacecraft control and data management procedures, all pre-programmed. There could be no last-minute corrections. The spacecraft was traveling at more than 49,000 kilometers per hour, and signals from Earth took close to 4.5 hours to reach the New Horizons probe. During the critical close approach, there was a 22-hour radio silence because the spacecraft could only make its scheduled observations with its high-gain antenna angled away from the Earth. Everything was committed to the 8 gigabytes of storage in the primary data recorder. To retrieve that data took 16 months. At a distance of 4.7 billion kilometers, the New Horizon data rates were down to 2 kilobits per second. Only the 70-meter dishes in NASA's Deep Space Network could detect the signal, and they could not work exclusively with New Horizons. New Horizons kept going into the icy debris field known as the Kuiper Belt. Even as it was still transmitting data from its Pluto encounter, engineers on the ground formulated a series of course adjustments that would take it past object MU-69, the first time a probe was targeted at a body unknown when the craft was launched. In January 2019, New Horizons encountered the Kuiper Belt object Arakoth, formerly known as Ultima Thule. At a distance of 6.6 billion kilometers, data from the spacecraft took 6 hours and 7 minutes to reach Earth, and the data rate had dropped to 500 bits per second. It's still trickling in. Finally, the most distant probe is Voyager 1. It was launched in 1977 and is now outside the solar system at a distance of 22 billion kilometers. The probe transmits data as it is registered, and the Deep Space Network tries to gather at least 16 hours per day of the data stream that comes in at 160 bits per minute. This is roughly equivalent to a telegrapher sending Morse code.